Okay, so welcome everybody to this session, and in the next 90 minutes we will be talking about advanced SQL techniques. And well, this is a schedule for the conference. You already know this. And a few words about me. My name is Gianluca Sartori, and I'm a SQL Server MVP. I've been working with SQL Server since version 7. And now I'm working as a DBA at a Formula One team. My blog can be found at spaghettidba.com. And if you want to follow me on Twitter, my handle is @spaghettidba. So what we will see in this session, we will discuss how to write high-performance code, why it's important to write high-performance code, why we focus on this. And then we will try to understand how to measure the performance, because it's all about performance. So we will have to measure what's fast, what's not fast, and we will have to find a way. And then we will introduce some powerful T-SQL constructs that will help you achieve this. And then we will discuss some famous T-SQL problems and their solutions. Okay, so first of all, writing high-performance code. Why we're interested in this? Because if we put all the different levels we can interact with when we're tuning performance on a pyramid, what we would have at the base would be the schema design. So a well-designed schema will support high-performance code and high-performance indexes, and everything built on the top will be performing better. But if we change something at this level, everything that sits on top of it will probably have to be changed as well. And on the opposite side, at the summit of the pyramid, we have server tuning. This is a very easy place to interact with if we want to tune performance. We just have to pull some levers and interact with some knobs at the server level. And what we will change here will not have an impact on what's below it. So it's going to be easy to interact with, but it will not likely improve performance very much. At the opposite side, changing things here is very difficult because everything that is on top has to be changed as well, but brings performance improvements that are very good. So in order to get the sweet spot, we have to choose something in between the two. Well, indexing is very easy to use to improve performance, but if you ever work with a third-party application where you cannot change the code, you probably know that working on indexing alone isn't often enough, because imagine you have some queries that don't use indexes because they contain non-sargable predicates. Indexing will not be the answer. Locking, well, it's interesting when you have to improve performance of the not of the application alone, but multiple sessions of the application. But if the code and the queries that are running in the system are fast, you will likely not have locking problems, because holding locks for a short time will help the parallelism of your system, so the concurrency in your system. So probably the best part to concentrate on to get the best performance improvements is the query optimization. So that's why it's important to focus on this level. So writing high-performance code means fighting an enemy, and the enemy is not Jeff Modern. If you don't know him, Jeff Mullen is this man with a beard. He wrote a lot of articles that you can find on SQL Server Central, and he's the man who came up with the Rebar acronym. Rebar means row by agonizing row, so basically the first thing that comes to your mind is a cursor. But it's not limited to cursors, it's everything that does things one row at a time. So we have while loops or application side cursors. So if you are doing things one row at a time from your C# code or from your PowerShell code, it doesn't make it less evil. And also we have some hidden forms of rebar, such as scalar and multi-statement functions that do things one row at a time or some rows at a time in the case of multi-statement functions. Why is rebar a bad thing? Well, we know that cursors don't scale well, but also the main reason why doing things one row at a time is not wise is because the execution strategy is fixed and it doesn't change when the data distribution changes. So accessing, when we have some joins, imagine, and you're accessing one table first and looping through all the rows, and then the second table and looping through all the rows with nested loops, you are deciding your fixed execution strategy, which is based on assumptions when you write the code. And when those assumptions change, when your code is live and you start having the data, objects such as the query optimizer can decide how to better access tables first, second, the right order to process the tables in your queries. And that cannot be done if you have rebar code. Okay, so in order to write more efficient code, we need to know all the constructs in the language. We need to know all the tools in your hands. And also you have to put no limits to your fantasy. That means that at some point you will come up with some crazy solutions, and it will be important not to overlook the crazy solutions because sometimes they do perform very well. And also we will have to recognize some code patterns, some famous problems, and know their solutions. So by knowing those problems, we will have to recognize them and know that there's a ready-made solution in order not to reinvent the wheel. And if that doesn't work, don't worry, because there's lots of people ready to help you. So there's the forums. SQL Server Central is a great place to start. There's DBA Stack Exchange, if you like the Q&A format. And also there's Twitter, if your question fits in 140 characters, which I don't think is possible, but a link fits. Okay, so it also takes some creativity. The same query can be expressed in many, many ways. And even the simplest problems have crazy solutions that you wouldn't think of looking at the problem for the first time. Let's see an example. I will count to 10. It's the simplest problem that comes to my mind. I just want to output 10 rows, and each of the 10 rows will contain a number between 1 and 10. So let's go and... Oh, no connection with the demos. Wait. So, share folders. Yep. Okay. Okay, I will show you 10 ways to produce 10 rows with the numbers between 1 and 10. You may think that it's impossible to have 10 ways to do that, but it is, in fact, really, really possible. So, first method, union all. It's very easy. We just have to union 10 different rows. Each has its number, 1, 2, 3, and we just need to run this to get 10 rows. Very easy. Method number 2, values. We could use the row constructor. So each row in the values clause has a different number. We just have to run this to get 10 values. So another possibility, SPT values. This is a table that has been floating around in SQL Server for a long time, since Sybase days, and it's a table that contains some numbers for reasons. It's used by SQL Server in some built-in store procedures and functions. So you just have to filter by the type P and take the numbers between 1 and 10. There's a number column, you just have to output that. So very, very easy. But again, this is an undocumented table, so another possibility would be to pull the 10 numbers from a known system table. In this case, we'll take sys all columns, and in order to get the 10 numbers, I just have to invoke the row number function and get the numbers. So what I can do is run this and get my 10 numbers. Okay, so suggestions, other ways? A cursor. Yep. So let's see if we have it. Do we have a cursor? No, we don't have it. Oh, we have a while loop. Pretty close. Okay, so a while loop. And what we do, we declare a variable, we increment it, we insert into a table variable, and then pull the numbers from the table variable. So let's see, and again, 10 rows. Suggestions? We've already used that. It's a values clause at the top. Well, I will show you a couple of more crazy ways to do that. On pivot, we have the numbers in columns. What we can do, this is in columns. We just have to turn this into rows, and it's pretty easy with unpivot. So let's do this, and it's 10 rows. And then another crazy method. We create an XML document on the fly with a for loop, and then we just have to call the nodes function to extract this from here, and ID, which is this. And each node will contain a number. So again, xquery, 10 rows. Recursive CTE. We just have to set the first number, and then all the subsequent numbers will be previous number plus 1. So let's run this. Again, 10 rows. And then CLR. Why not? We just have to have some code, C# code that returns some numbers. In this case, I will not show you the code, but it's a stupid while loop. And what I have here, 10 rows. The while loop, it's already done. The most obvious way to do that, we could have a table with numbers. It's a Tolly table. We will go back to this shortly. And if the numbers are already available, we just have to pull them. So again, 10 rows. So what we have seen proves just the point that there's many ways to solve problems, and even stupid problems like pulling 10 rows from the database can be solved in multiple ways. So don't focus on a single solution, and when performance is not acceptable, try in many ways, and some of those will perform well. Okay, regarding performance, one of the things we have to do is make sure that we are measuring things in the correct way. So we have seen 10 ways to extract 10 numbers from the database. Which one performs best? We don't know, because we would have to measure that. And the easiest way to measure the execution time is to look at the execution time that we have here in the bottom right corner of Management Studio. Here we have an execution time, but this doesn't take everything that is under 1 second into account, so it will always be 0 seconds. So it's not good enough for what we have to do in this case. Also, that execution time contains the time it takes to transfer the data from SQL Server to the client machine. And in case it's a big table, so lots of rows or lots of columns, that time will be even more than the time it takes to execute the query itself. And also, that execution time in Management Studio contains the time it takes to format the data into the grid. So it doesn't only show the real execution time of the query. So one thing we could do is discard the results. One of the possibilities that we have here in Management Studio. If you right-click here, you have Query Options, Grid. You can discard results after execution. But again, we cannot measure anything below 1 second, so it's not the correct solution. And also, if we discard the results, it also discards the messages, which is where you get the information from set statistics time, which is another possibility. So really, we're stuck. The only way to measure correctly the performance is to trace the execution with a SQL trace or an extended event session, and then pull the time from that trace or extended event session. Also, a single execution could not tell the whole truth. So in case we had different methods and we want to compare them, we want to execute the same queries, the same set of queries multiple times, because many things could go wrong. In case of CLR procedures, example, there's a startup time that it takes to load the CLR procedure in memory for the first time. Or if you have multiple executions of something that has parallel queries, the level of parallelism that you get in different execution could be different. So that's one of the things to take into account. And what you do is you repeat the execution multiple times, you average the times, and you take that average into account. Also, one thing that could be worth doing is warming up the cache, because the first time you execute something, you have to pull the data from disk and bring it to memory. And from that moment on, the data will be pulled directly from memory. And it depends on what will happen in production. If that piece of code will run against data that will probably be in the cache already in production, you will have to warm up the cache before taking your measurements. Otherwise, you keep it in disk, or you can also force discarding the cache completely. Okay, so I will show you a script that I use to measure performance this way. So let's go and see here what we have. This is a PowerShell script. And basically what it does is it creates a trace. It captures this event, 41, which means statement completed, and some columns, and these are the columns that we need to capture CPU time, execution time, reads and writes, and whatever is interesting for us to measure. And then we execute the script that is taken as a parameter, and the script contains all the different methods we need to compare one against each other, and it runs the script multiple times. This iterations variable is the number of times we execute the script. And after that, we stop the trace and we query the trace. And what we want to do here is we group on text data, which is the text of the query, and we calculate the duration, reads, writes, and row counts. Okay, and we get also a query number. So let's try and run this. In order to run it, we just have to decide which script to fit it, so some parameters, the server to attach to, the database name, the name of the script, and the number of iterations. So let's try and run this. It's harness invoke, and what it does, it runs the script, in this case 10 times, and in this case it's comparing different methods. We will get to that script later, but it's different methods to do the same thing. So let's see what we have here. This is the output, and what we get is different executions of this. What we want to compare is the first query with the last one, because it's different methods to do the same thing. The other two, this and this, are just support, but they create functions, so it's not the actual code. What we want to compare is this and this. So it's pretty clear which one wins in this case. So you could also compare reads and writes and whatever is meaningful for you. Okay. Everything clear so far? Great. So let's close this and also this. Fantastic. Great, so let's go to some of the tools that will help you achieve better code performance. One of the most overused tools in T-SQL is the apply operator. Underused tool is the apply operator. So you probably already know the apply operator. It's something that is used to apply a function to an input set. So you have your input set, you invoke the apply tabular function, tabular function, and what is returned by the function is applied to the input set. So in this case, we have 2 rows and 2 columns. To apply to a single row, single column, this becomes a set of 2 rows and 3 columns. So pretty easy. The most common use of the apply operator for... how many of you worked with versions prior SQL Server 2005, so SQL Server 2000 or SQL Server 7? Okay, somebody. So what you had before SQL Server 2005 was something different. There was no apply. So when you had tabular functions, multi-statement table value functions or inline table value functions, the only way to use them was querying them. There was no way to apply them to an input set. With SQL Server 2005, the apply operator was introduced, so what you could do, you could apply a function to an input set, so basically a query, and you could use some of the columns in the input set as a parameter, a correlation anchor for the function. And this is the most typical use of the apply operator. Also is useful for changing some UDFs, so scalar function, into inline table value functions, which is something you couldn't do in SQL Server 2000. Another use of the apply operator, which is often overlooked, is this use where the function is not saved in the database, but it's defined inline inside the query itself. So basically what you do is you apply a function that you open here with a parenthesis, you close it here, and you define the function in line with the query. And the anchor here, the correlation, is done by using columns of the input set. This can often be rewritten as a join, and in fact what the optimizer will end up doing in most cases will be reordering this kind of query as if it was written as a join. When the optimizer is unable to do this, the only possible join strategy between the input set and the function is a nested loop. When the optimizer is able to translate this into a join, it will also be able to use different join strategies, such as hash join or merge join. Okay, so let's go through this quickly with some demos. Okay, so here we have a query that basically goes to all the details and all the header, joins the two tables, and then applies a scalar function. This function, UFN get product list price, is available in the AdventureWorks database, so it's not my my code. So if we go here to wrong instance. If we go here to scalar functions, this is a function. Let's have a look at what it does. Basically, it goes to production product and product list price history, and it pulls some data. Basically, what it does, it returns a value, which is of the type money, by doing this query. And the correlation between the two is done by passing these two parameters from the outer query. So this, if we execute this, it takes around 2 seconds to execute. What we can do is we can improve the performance of this query by changing that function into an inline table value function. Why it performs better? Because if we do something like this, trace querying in Profiler, you will see that we have 121,000 rows returned by this query, and each of these rows invokes the scalar function, which reads some data from the database. So when we run this, you see that we are capturing all the executions of the scalar function, and this will take ages now to execute because we are tracing it, which slows down a lot. But what we have here is that we are executing that query in the function 121,000 times, which is not ideal. Okay. So what we want to do, we can create an inline table value function with inside the same exact code we had in the scalar function, but this time, instead of returning money, we return a table. And that table is what this statement returns, which is the same statement we had before. And this time, if we create this and we invoke it using the apply operator, this time what we have is it executes in 0 seconds according to this. But looking at set statistics time here, what we have is over 100 milliseconds, which is a lot less than what we had before. So what we have here, input set, apply, and this is how it works. Okay, let's have another example. Another thing you could do with the apply operator, you could use it combining it with other constructs, such as the top operator. So, example, imagine you have to pull from the database the most recent order for a customer. So for a single customer, it's easy. You just have to filter for the customer ID you're interested in, and you order by, order date, and sales order ID, and you use top one to filter the rows returned. So in this case, it's very easy. But imagine that you have to do that for all the customers. It becomes a little bit more complicated. So using just standard tools, SQL 92, joins and grouping and whatever, it can be done, but it becomes a bit complicated. So in this case, we can do, we can go to the customer table to pull all the customer, and then we have to get the maximum order date here, maximum order date, and then we have to extract the maximum order ID in a subquery, and then we have to join on customer ID from this query, so M, this is M that we have here, and customer in order to join the two sets and get the maximum order for each one. Let's see if it works. It works. But it's a bit complicated. So another way to do that, you could have different joins. So we have a first join with a subquery that gets the maximum order date grouped by customer ID, and then we have a second, and this is joined on the customer ID column. And the second join with a subquery, this time it takes the maximum sales order ID and joins on customer ID and order date. But again, it's a bit complicated, and we're accessing the same table, sales order header, multiple times. So there must be a better solution to this. Also, imagine that you want to return another column from the sales order header table. So in this case, imagine you want to pull total due. You have to add another subquery. And if you want to take the ship date, it's another subquery. So we're hitting the sales order header table multiple times for no real reason. So here we have another field, another column, so the status. So another access to the table. Imagine you have a situation like that. So where exists can be used to join to the sales order header table. So you just join on the customer ID, and then you could limit the rows returned by this sales order header join by correlating it with this where exists, with this subquery. And this is the one that returns the maximum order date and maximum sales order ID that we had in the first query. This is correlation. This is a predicate we're correlating on. And this works as well, but again, we're hitting sales order header multiple times. Let's try to find a solution that hits the table just once. We could use apply to go to the table, sales order header, just once, and do exactly the same thing we did with the query, that it returns data for one customer, and that customer is the one that we have in the correlation predicate, this one. So this is what we have in this case using the apply operator. If we take a look at the execution plan, as we said, this uses nested loops to correlate the input set with the function. This is because top is a non-relational operator, and the only way to use a non-relational operator in a subquery is by applying the function with nested loops. So let's try to see if there's another way to express this query. We could use row number instead of top to pull just one row. So we use here row number. We're filtering the same way, so this time we're filtering for customer ID, the one that comes from this query, so the customer here. Here it is. So this isn't the predicate filter. And then here we filter for row number equals 1, so we just get the first row. It's the same thing as top. So let's try to see if it returns correct data. Yes, but again, we have nested loops. Oh, doesn't work very well. This is because of the position of the filter predicate here for row number equals 1. It is not in the right position, because we're first filtering for customer ID, and we're doing this multiple times. So in order to avoid that, we could use a partition by part of the row number. So we're partitioning for customer ID, ordering for order date, and sales order ID descending. And here we apply the filter for row number equals 1 and customer ID of the correlation predicate. And this will produce a different execution plan with a merge join. And this will perform much better. Okay, everything clear so far? Good. Another thing you could do with apply is a different solution to the unpivot problem. So imagine you have a registrations table with people that register to some, I just need to use the right database. People that register to a website and they have a date they join, and in case a date they decide to leave, cancel their registration. So if you want that in rows instead of columns, you could use unpivot with this classic syntax. So unpivot, event date for event type in date join, date left. And what you get here is this. So you have columns that became rows. This was the first row, this was the second row, and so on. Another possibility to do that is using apply. Apply and values, the row constructor allows us to do the same thing as unpivot by doing this. So we create some rows with the row constructor, and first row contains the date joined column and the join constant. So we're doing the same thing that the pivot did. And the second row contains date left and the left constant. And what we have here is the same exact result. Okay, so rows made like this. Is it clear how it's working? Good. Okay, this method is slightly faster than plain unpivot with the unpivot syntax. Okay, so apply. We have seen that it has some potential. And then another tool that is very useful is the overclose. The overclose, you probably already know that, defines some windows of rows. They are defined in the partition part of the overclose. And it applies a function to each window. So we have ranking functions, such as row number, rank, dense rank, and so on, and aggregation functions such as minimum, maximum, and so on, and some analytic functions, lag, lead, first value, last value, and so on. And the overclose was introduced in SQL Server 2005 as well, but we have some major improvements in 2012. Because we had support for rows and range. Rows and range basically allow calculating many things, but the most important ones are running aggregates, so basically running totals. What does it mean? If I have some orders or some numbers from a table, and I want to sum those numbers and take the sum until that point, what I will do is a running total. So will sum first row with nothing, second row with first row, third row with second and first row, fourth with third, second and first, and so on. And before having rows and range in the overclose, so before SQL Server 2012, this one was one of the most complex problems to solve in T-SQL. And you could do that with cursors, and cursors actually perform very well in this case. Oh, you could do triangular joins. What does it mean, triangular joins? Each row is joined with previous rows, and so that means that the first is joined with nothing, the second with one, the third with two rows, and this goes on and creates a triangle. So that's why it's called a triangular join. Then we have two solutions that are called the Quirky Update and Quirky XML. Quirky, the name says it all. It's dangerous, it's not guaranteed to work, but it actually does work. And it's based on observation, the fact that it works, and it's not based on any documented behavior. Basically what it does, it takes advantage of a quirk in the update syntax, which allows you to assign some value at the same time to a column and to a variable. And that variable can be incremented when you reach the next row. The technique is documented in one of the articles by Jeff Molden, so you have the link. When you download the slides, you will find the Quirky Update. Oh, you can look it up on Google. First hit will be that article by Jeff Molden. Quirky XML does the same thing, but it creates an XML document on the fly while scanning all the rows, and then you just have to query the XML to get the results. But so really ugly. Okay, so let's have a demo here of what the overclose does. So first of all, the basics. Ranking functions. You could have here row number or rank or dense rank, and each of these will calculate a rank for each of the rows. So if we run this in the correct database again, what it does is it gives a rank to each row, and this is what we have. So we're ordering by quantity. So here the quantity is 1, and the rank will be 1 for all the orders. So let's go to where it breaks, because it's more meaningful. In this case, we have that rank, when it changes, here has 13, and there's a hole in between because this is row 13. If we use dense rank, we don't have the hole, there's no gap here, so it goes 1, 2, and so on with dense rank. So this is the basics. Let's go through this very quickly. You could also partition by something, so this defines the window on which the overclose is applied. So if you partition this by sales order ID, this means that every time the sales order ID changes, the ranks are reset and you restart from 1. Okay, let's try and run this and see the difference. So here we have it. So this is the first order. As you can see, you have a row number here, and then it resets and restarts here 1, 2. And again, same thing with a rank and dense rank. Okay. Wait, what are we? Okay, you could also run window aggregates. So you could execute this and get the average, sum, maximum, and count on a window. So you could define here a window by using the partition by part of the overclose. What you get here is the sum, or average, or whatever, based on a window. And the window starts here, ends here, and you have average and total and maximum and count. And this is very, very basic. So you can use this to get, example, the row with the highest quantity for each order. Very similar to what we had with the top example, and apply. In fact, here we can define a CTE with row number over partition by sales order ID. So I'm resetting this every time the order ID changes. Order by order quantity, and again I take just the one with row number equals 1, so the first with most quantity, and this is what I get, just the first row. Okay, the same thing could be done without the overclose. Obviously, you just have to run a subquery, and you can do that with a top, so as we have done before. So let's go to a more meaningful example. In this case, we're doing running aggregates, running totals. Okay, first use of aggregates in the overclose, the simplest one, is this. Holy crap. You can define an empty window, so over nothing, and it does a sum. This means that it does it performs a sum over the whole input set. So it means the sum of the whole table in this case. If we expand that a bit, we could add this order by clause inside the overclose. So what we have here is a running sum, a running total. This was introduced in SQL Server 2012. So let's have a look at what this does. Okay, it's order by sales order detail ID. This means that sales order detail ID is a column we're sorting on, and we will have a running sum. First row 3, second row 3, running total 6. Third row 2, so it's 6 and 2, 8, and so on. Okay, and this is very, very useful in many situations. What we have here, over order by sales order detail ID, actually means this. Means order by sales order detail ID, range unbounded preceding. This is the default of the overclose. This means consider all the rows in a range that starts with the preceding row and current row. So extended syntax is range between unbounded preceding and current row. And this means that the range is based on the value of the column we're using in the order by clause. There's another mode for this, which is the rows mode. And range is based on the value, and rows is based on the physical position of the rows. So it means that ties will be treated differently. Range will treat ties returning the same value, and rows will rank the rows differently. So this is the other possibility for the overclose. Order by says order detail ID, rows unbounded preceding. With extended syntax, it means rows between unbounded preceding and current row. What's the difference performance-wise? Range uses a spool that goes to disk, and rows uses a spool that goes to memory, and it makes a big difference in terms of performance. Okay, so if we run this and we compare the two execution plans, you will see that we have spools in different positions and different kind of spools here. Okay. So before SQL Server 2012, one of the possibilities was a triangular join. You have it here as an example. So what you had here, the running sum, was the sum of the order quantity from, again, the same table, so orders, and the correlation predicate was says order detail ID less or equal the one in the correlation table, the outer table. Okay, everything clear so far? Questions? Good. Perfect. So with these tools, what we can do is we can try to solve some of the well-known problems that we have in SQL Server, in T-SQL actually. One of these problems is the islands and gaps problem. So what's the idea? Imagine you have a table with some numbers in it, and the numbers go from 1 to some value, and they're all consecutive numbers. Imagine that at some point you delete some of the numbers. It's supposed to be gray, but I don't see the difference from here. 5 should be gray, 9 should be gray. Oh well. So what you have here is some islands, which is the values that are not missing, consecutive values, and the gaps are the values that are missing. So in order to identify these islands and gaps, there are some solutions. What you want to obtain in the end is something like this. So the first island is the one between 1 and 4. There's a gap here, it's the first gap, and then second island and third island, and these are the gaps. So one thing to note, you always have one gap less than the number of islands. Okay, how to do that in T-SQL? Let's try and find this. Okay, first of all we need a table, and this table we will call it the numbers table. It just has one row, one column, sorry, and we will pull some numbers from the Tolly table. We will see that shortly, and we will delete some rows. We will insert 10 million rows and delete some. Well, it's not random rows. We will use top with order by checksum new ID. This is not really random rows. Ask Dan Sarka if you want to know more. And then we will make sure that we also delete row number 9, because it's handy to have it at the beginning of the set. So let's do this. So when this finishes, we can look at the numbers we have in the numbers table. Regarding the randomness of the checksum new ID, Dan Sarka says it's not really random. Had a presentation about that. And not only that, but he's a mathematician. I am not, so if you want the explanation for that, ask Dan. So it's taken a long time. Okay, we have 10 million rows. Let's have a look at the rows. Here we have a gap. See, 9 is missing, and there's some number missing somewhere, and we have to identify where the gaps are. So solutions for that. Okay, let's have a look at the numbers table. Ranking some of the rows, we will use a dense rank function over order by the number, and then we will observe something. Again, I need to go to the correct database. This helps a lot. So what we have here, we have first row, second row, and so on. And then if we rank these rows, we get the same number, so 1, 2, 3, and so on. At some point, when we have a gap, here, we will have that the number and its rank will not be equal anymore, because we have a gap. So if we subtract the rank from the number, what we get is a group, is a number that keeps equal for the whole island, and this is what we are after. So 1 minus 1 0 and 2 and 2 0, 3 and 3 0, and so on. Here we have a gap, so we have 10 and 9 1, 11 and 10 1, 12 and 11 1, and so on. So this is exactly what we want to obtain, and this is based on this. So dense rank and n minus dense rank. Okay, let's put this in a common table expression. We just want to know where the islands start and where they end. So here we just need to take minimum and maximum grouping on the group, so the column that we created by subtracting the rank and the value. So here it is. And what we will get here is exactly the solution to the island problem. So here we have some ranges. The range starts at 1 and ends at 8, and then it starts at 10 and goes to 7062, and so on. So using the overclose, we solve the island problem. The opposite problem, so identifying where the gaps are, is again based on the overclose. And there's a famous solution. It's by Itzik Ben-Gan, and this is based on not based on the overclose, but it's based on subqueries. So what it does here, it filters where not exists the next number. So this is the table you're querying, and this means take the rows that don't have the next number, and that the n plus 1 next number, the one that is missing, is what I want to return, and the end of the range will be the next number available in the table, and I limit this for number less than the maximum number in the numbers table, obviously. So this performs very well. Let's have a look with statistics time. Even if it accesses a table 3 times, it performs very well. Let's have a look at the messages here. We have CPU time of 2.5 seconds, roughly. There's another possible solution. We had, since SQL Server 2012, the lead function in the overclose. Lead means next value based on the order provided in the overclose. So this means that lead n over order by n means next value from the table. And it should perform well, but it doesn't. And if you take a look at this, oh well, no, it cannot be. Okay, it's 10 seconds. 10 seconds over 10 million rows, so it is not really performing well. There's another solution. This is a solution by Dwayne Camps, and this solution is based on the island solution, and this basically takes the island solution and cross-apply values, range start, range end. Basically it turns the start and the end from columns to rows, and then just takes the ones that have 2 rows, and in this case it performs quite fast, but again not as fast as InsideSQL's solution. So let's have a look. It's 3.5 seconds roughly again, so it works well, but not as well as InsideSQL's solution, so keep this in mind. Okay, well, using the island and its solution, you could solve some interesting problems, such as identifying sequences of consecutive characters in a string. And this is a solution for that. I will not explain you this because it doesn't make sense, but it's an example. You have it in the downloads, so if you download the code you can have a look. And another thing you could do, which is again useless but interesting in a way, you could parse a date using the island solution. Each piece of date is in fact an island, because if you pass a format string that you will use to parse a date from a string, that format string will contain year, 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 month, month, day, day, and those are islands in fact. So that means that using the start and end of the islands, you can take characters from the input date and return a date. And this is all based on different islands. Again, it's super long code, but what it does in the end is you can use this to parse dates from some characters here using an inline table value functions using the islands solution. Okay. Another tool that comes very handy is the Tolly table. The Tolly table is basically a simple table that contains one column and it has numbers. And it's a Swiss Army knife for T-SQL. It's used to solve many, many problems. And the most famous ones are string splitting or exploding some rows for a quantity. So it can be a permanent table. It can be in your database, a table named Tolly that contains numbers. In this case, it has to be read from disk and then from memory. So you will have physical and logical reads when you use it in your code. Can also be defined on inline. So in that case, you will not have logical reads, and will be a common table expression in your query or an inline table value function in your database. String splitting using the totally table. Imagine that you have a string like this with some commas that separate your values. And you could think of this vertical, so it fits well with thinking of a table. In a table, numbers are in vertical. So if you think of it this way, it's easy to understand how you can use a totally table with numbers to identify the different pieces, the tokens in the string. So using the substring function, well, filtering for the comma, you identify these rows, and you just have to take these rows again in the substring to extract the tokens from the string. And there's a function that you can find on SQL Server Central, and also many other string split algorithms that are illustrated here on SQLperformance.com. There's an article by Aaron Bertrand, and he also highlights the different performance of the solution for string splitting. The best way to split strings is avoid splitting strings because it's a strong indicator that you're violating first normal form. So think twice before inserting data with commas in your database. If you have to do that, use a CLR procedure because T-SQL is not the best tool to do string manipulation. Also, in SQL Server 2016, we have a new function, string split, which is basically a built-in CLR function, and you can use that to split your strings in SQL Server 2016. So let's have a look very quickly because time is running out. So string splitting. This is a function by Jeff Modern. It's pretty popular. It's delimited split 8K. And I will not go through the code. It uses a totally table. It's a dynamic totally table. I'm using this getTotally function. And then it takes a substring to get the delimiters, and again substring to extract the various token you have in the string. So let's create this, and we can use the delimited split 8K to split this input, and what we get is all the items in the input string. So let's expand this to see all the pieces. Okay, so we have string 1, 2, 3, 4, 5, 6, 7, and the item number. Okay, pretty easy to use. And if you have SQL Server 2016, you have string split that does the same thing. So let's change the connection and connect to a SQL Server 2016 instance. It works on any database with compatibility level 130 or more. And what it does here, same thing. This time I use cross-apply string split, and what it returns is all the rows. But if you look at this, you will notice that there's no item number returned this time. So this is one of the huge limitations of the string split function in 2016. One way to overcome that is by using an artificial item number that you create using row number over order by select null. This select null basically tells SQL Server not to order the rows obtained by this set, from this set, and it will preserve the natural order used to return the rows from string split. It's not guaranteed to work, but again, based on observation, it works. Don't rely on that. At some point, I hope that Microsoft will fix the string split function. But if you want to use that, again, you can obtain the item number using that trick. So here we have the item number again. Okay, the opposite problem, so concatenating strings, is pretty famous again. You could use for XML path to concatenate strings over multiple rows. It's a hack. It produces an XML document, and you just have to query that to get the results of the concatenation. Again, we have several methods for string concatenation, and the best method is using a CLR aggregate. There's an article here that describes all the methods. It also contains a source code for a CLR aggregate that does exactly this. There's Matiala that has a whole 60 minutes session exactly on this. So it's a complex topic. Go here and read it up on this article because it's interesting. So a quick demo on string concatenation. And string concatenation. Simple concatenation is pretty simple. So if I want to concatenate all the databases from sys databases, what I do here is I use XML path empty and use stuff to take away the first character, the first comma. So what I get here is concatenation of all the databases. One thing to watch out for is entitization. Here everything works because I didn't have any weird characters in my database names. But if I create this database with an angular parenthesis, what I get with this code is something that doesn't work anymore because I have it didn't work. So one way to avoid that is, instead of converting it directly to unvarchar, we use value, we keep it as XML. So for XML path type, this means return it as XML, and then we query the XML with the value function, and in this case it doesn't get turned into an entity. So here we have the correct result. So again, it's a hack, but in order to use a hack, use it correctly, otherwise it won't work. Okay, there's another example here that we don't have time to go through, but imagine that you have to concatenate rows across columns. So imagine that you have some sentences in different tables. Wrong database, wrong instance. InsideSQL. Okay. Imagine that you have some sentences and you put the different translations of the lorem ipsum text in different columns. No. Okay. So what you have here is Latin, English and Italian version of the lorem ipsum. So if you want to concatenate all the different languages in a single pass, it gets a bit complicated. So you could use some different, with some creativity, you can unpivot the different rows in order to get them all in a single column, and then group them and concatenate the different languages, and then repivot the results to get them in different columns. I will not go through this code because it would take a lot of time, but this is what you will get. You have it in the examples. If you're interested in this, you can have a look. Okay, so another concept I want to show you is the set-based iteration. Set-based iteration basically means that there are problems that are difficult to solve with pure set-based solutions because the pure set-based solution either is incredibly complex to get it perfect, or is not even possible to obtain. So what we do is we use blocks of set-based code to get consecutive approximations of the solutions until we get the perfect solution we're looking for. So what I will show you here is stock assignment with a set-based iteration. What does it mean? Imagine that you have a warehouse with some items, with some products and some orders, and you have to find which products in your orders are covered by some stock in your warehouse. So what you will do here is you will look for sufficient stock and try to assign some stock to each row in your orders in order to ship those orders. So first of all, we need a trolley table. So let's create this. And then I will show you a pure set-based solution to this. So what you do here is you can go. Oh, so here are the rules. The orders are shipped looking the due date column in the orders. So the ones that have a previous due date are shipped first, and only complete rows are shipped. So that means that if I have a quantity of 5 and I have 3 in the warehouse, I don't ship the row. I don't ship the 3 I have. I wait until I have all the 5 available. So how can you identify this? You can use Overclosed. You can partition on product ID your orders, and then you order by due date, because this is the precedence for orders, and then we join with a trolley table and we explode the quantity with the trolley table. So if I have a quantity of 5, I will get 5 rows. And I do the same thing for the inventory. So I look at what I have here in production, product inventory. I partition by product ID to get a row ID product. And I explode the rows using a trolley table. So it's 2 other techniques that we have seen today. And the assignment of the 2 products and in inventory and in orders will be the ones that have matching row ID. Is it clear enough what I'm doing here? So. Okay, I'm joining inventory. So inventory is what I have here, exploded by quantity. Let's have a look at what happens. So quantity is 400. I will have 408 rows like this, and each has a row ID. Okay, Same thing with the orders. I join the two by product ID and the ID I just calculated, and I match the two, okay? And I filter this to get just complete rows. The ones that are not fully covered by inventory, I will discard them. And if I run this, it's very quick, even if I have 121,000 other rows. But what I get here is 23,545 rows returned. And let's compare this with a cursor-based solution. A cursor-based solution basically would just go through all the orders, and if there's enough quantity, enough inventory to cover that, will decrement the inventory and process the rows one by one. So it's guaranteed to be working. Let's do this. I will not show you the code. It's very, very simple. You have it in the samples you can download. It takes quite a lot of time because it takes around 20 seconds last time I tried. And what it does, it produces, okay, 23,715 rows. So that means that the pure set-based solution didn't produce all the rows we were looking for. Why? Because the cursor solution, when one row isn't completely covered by the inventory, doesn't skip it. It will assign it to a next order. But the set-based solution will use that quantity even if at the end of the solution that rows that are not completely covered by stock are discarded. So we are losing some stock during that operation. So what can we do? We can combine a set-based solution with a loop, and what we have here is 3 different methods to do that. You have it in your downloads. Let's see the first one. So we will use a temporary table to store the results. Rules are the same. And what we do here is, while this method produces rows, we keep inserting into the temporary table. And what we do here, again, we explode the rows with the same technique we used before, so orders multiplied by the quantity. We exclude the rows that are already assigned, so the ones in the results table, and rows with sufficient stock. Inventory, same thing. We're exploding this with the tally table, but we subtract the quantity that we already have assigned in the results table, and again exploded by the tally table, and only products actually present in the orders. And here I assigned the two, I combine the two things, inserting into the results table. And this, rows affected, is a row count. So while this produces rows, I keep inserting into the results. And this is not as quick as a set-based single-pass solution, but in 7 seconds, so half the time of the cursor solution, it produces all the rows I'm looking for. So it's a way to combine set-based with procedural code to refine a solution on the fly. Okay, so some links for you. Something about apply and over. You have some interesting articles here you can look up. And something about the tally table, string splitting. Something about running totals, islands and gaps. And bin packing is an interesting problem. Hugo has great solutions about bin packing, and they're all set-based iteration. Actually, the name set-based iteration is Hugo came up with a name, so credit to him. And basically, if you have questions, I'm here to answer your questions. No questions, so thank you very much.